Okay, welcome to lecture 2.10. Okay, I finished actually the substance of session 2. Now, is what I typically do is I reserve the last 20 minutes or so of every session to discuss the paper that is coming up. And the paper that we're going to do in session 3 is the Levitt-Porter paper. And so there's some things about it that I think it's useful, at least some things I had difficulty when I first tried to read it. And I want to explain some things to you that hopefully you won't make the same mistakes when you try to read it. So here is the idea and some definitions. Let's go through some of these. So first, in that paper, they define Big D. Actually, I'm going to define Big D as it's the subscript for being drunk. So the Levitt-Porter paper is like trying to estimate how many people on the road at any given time are under the influence of alcohol. Maybe it's drugs too. I can't remember. But they call it D, and technically it means under the influence. And I think that it included things if you had a blood alcohol level of, God, I can't even remember the numbers. I think in most states it's 0.8%, 0.8% or 0, or God, is that right? 0.08, I can't remember. But 8 something or 10 something is, I think, typically for the states, whether you're drunk or not, or under the influence. And I think the Levitt and Snyder, they included cases where you were 2/3 that amount. So you were legal, but driving under the influence. I can't remember the exact number, but it's the key thing is it's a dichotomy. Okay, whether you're, I'm going to say drunk or not. When I say drunk, I'm really meaning what Levitt and Porter say, under the influence, which is might not really mean drunk, but it's a dichotomous variable. Whether you are or are not, okay, it does not measure the extent to which you've been drinking alcohol or whatever. Okay, D is drunk. S just stands for sober. Okay, and then they write in total, and that stands for total number of drivers. And then N sub D equals number of drunk drivers. And they're going to do things like it's at any given moment in time. And more specific, they're going to estimate for various hours of the week. And so I should look this up. They estimate, for instance, like from 11 p.m. to 12 p.m. on Friday night, what percent of the drivers are drunk. And so first we'll define ND, that's the number of drivers who are drunk, and then we'll have NS equals number of sober drivers at that given point. Okay. Okay, so what things like this, percent of drivers who are drunk is just going to equal ND divided by ND plus NS. You know what? I don't think I'm going to use that in total in the rest of my lecture. I'm just going to right, NS plus ND equals in total. Then I'm going to drop in total and just use ND plus NS. Pretty sure throughout my lecture I'm going to do that. Okay. Here's their data. No, wait. No, first off, it's useful to define what Levitt and Porter mean when two cars interact. So they're a little nebulous on what that means. And here is the best way to think about it. Here's what went through my mind. And this was to think, suppose there's only one road in the entire, let's make it double yellow line. There's only one road I swear I think about a road near my house where it's single lane on each side. There's a double yellow line. It's kind of curvy. There's no shoulder, so it's kind of a dangerous road. And I think anytime there's an interaction, it's when two cars pass each other. Okay. So the Levitt and Porter paper, this is more generally, it's all roads. And so it's more general than I'm going to think about, but it's useful if you suppose there's only one road. Okay, it's when two cars interact, and let's call this the eastbound driver and this the westbound driver. Okay, so that road goes east-west. Okay, and so there's north-south roads. That's the way I like to think of this, and I think it's useful if you think of it that way. Okay. The data, turns out the data that they got only involved fatal crashes. And so the idea behind this, and later I'm going to show you an email from Steve Levitt. So I met Steve when he was a grad student at MIT. This was 1994. And I met him when he was still a grad student. I was like starting my third year as an assistant professor. I met him when he's young, and to my credit, I predicted very early on that Steve's going to win a Nobel Prize someday. I said soon after meeting him. Steve sent me an email, and I asked him, how'd you get this idea? This is a really clever idea. And the idea is, he said, no one knows how many drunk drivers are out there. You set up these roadblocks, but there's all kinds of sample selection problems. People could learn about the roadblocks. Who knows if that's really a representative sample of the drivers that are currently out on the roads at that period. So Steve had the idea. Said, well, let's look at fatal car crashes. And so, you'll have these statistics like if the fatal car crashes, 10% of the cases at this given hour, at least one of the drivers was drunk. And so some people would infer, well, that means about 10% of the drivers are drunk at any given time. So, no, you can't do that because drunk drivers are worse drivers than sober drivers. It's probably less than 10%. So, how do you get that? And Steve had the great idea that you treat these cars as if they're like an exogenous event. And if there's a drunk driver going east, he or she could swerve and hit the driver going west. Okay, now, those were said, given that this guy is drunk, it's an exogenous event, whether he hits the other person there. It's just random whether there happens to be a car driving at that time. And if he does, it's almost like a random sample. We can look to see this other driver. Is the other driver drunk? And so Steve said he had this idea that there's got to be a way to use, compare car crashes and look to compare the number of 0 drivers that are drunk versus only 1 driver that's drunk versus 2 drivers that are drunk. And there's got to be a way to get an estimate of how many at any given time among the population of cars is the driver drunk. Okay. So that's the idea. Steve said, well, let's look only at fatal car crashes. And it turns out there's pretty good data on whether each of the drivers is drunk or not. So that's the data they have. Okay, next, here's another definition. Okay, let's call it theta sub d. And this equals given an interaction. Okay, so if given a case where 2 cars pass each other on this one road we're thinking about, okay, and given, now this is going to be given that one of the drivers is drunk, that a particular one. So what I'm going to do now is I'm going to say, let's look only now at the eastbound driver. Okay, so this is given an interaction and given that the eastbound driver is drunk. Okay. Theta D is the probability probability of a mistake. Okay. And that mistake, this means it makes their data set, i.e. a fatal crash. Okay, of a mistake. Okay, and another way of saying this is i.e. the probability that at least one the eastbound or the probability. No, you know what? I've written this wrong. Given an interaction and given that the eastbound driver is drunk, this is the probability. I'm so sorry. I looked at the wrong spot on my notes. The probability that he, whatever it is, he or she makes a mistake. Makes a mistake. Okay, in this, mistake, i.e., causes a fatal crash. Okay, that's theta D. Now, I said given an interaction, theta D is the probability, if given that the eastbound driver is drunk, theta D is the probability that the eastbound driver makes a mistake. If he swerves across the yellow line. Given an interaction, so that means there's another car on the other side. It's the probability that he causes a mistake. Now, theta D also is the definition of the other case. So, given that the westbound driver, so it's the opposite, given that the westbound driver is drunk, theta D is the probability that the westbound driver drives across the yellow line and causes a fatal mistake. Okay. Theta S just equals the same stuff, except wherever I wrote drunk, replace it with sober. Okay, so it's given that if, say, the eastbound driver, we know he's sober, theta S is the probability that he's going to make a mistake. Okay. Okay. Got that. Now, next thing. Okay. Let's define this. Okay. If the eastbound driver is type I, okay, i.e. D or S. Okay. So I represents a D or S, and westbound driver is type J. Okay, again, it's a D or S. The probability of a mistake, and in here mistake means a fatal crash. Probability of a mistake, i.e. a fatal crash. Okay. So, by the way, mistake is a synonym for fatal crash. So, if there's a mistake that happens, that's a necessary and sufficient condition. If a driver makes a mistake, Levitt and Porter's definition, that means there's a fatal crash. If there's a fatal crash, that by their definition, that means at least one of the drivers made a mistake. Okay. So the eastbound driver, the probability of mistake equals, okay, probability that both made a mistake. Okay, so that's one way you can get a fatal crash, plus theta I times 1 minus theta j, and this is probability eastbound made a mistake, comma, westbound didn't. And then it's also, then the third way you can get a mistake is 1 minus theta I, the probability the eastbound did not make a mistake, but the westbound did make a mistake. Okay. Okay. Next, if you do the math on this, you can verify for yourself that this all simplifies to theta I plus theta j minus theta I theta j. Okay. All right. So that's what we get. So this is, given the types of drivers, this is the probability of a fatal mistake. Okay. Okay. Theta I is on either theta d or theta s is on order of 1 in a billion. Okay. So any two cars pass, the probability that they're going to have a fatal crash is very, very low. It's something like, how is this? I think for every 100 million miles you drive, there's an expectation one traffic death per. So you think about that, 100 million miles, how many cars you pass? It's a lot. It's actually probably something like on the order of 1 in 10 billion, on the order of 1 in 100 billion. So what Levitt and Porter do is they say, therefore, we'll assume theta I times theta j equals 0. So it's something like 1 in a quadrillion. They're going to say 1 and it's 0. I'm not 100% certain that's the proper thing to do. And in fact, I think there may be a dissertation chapter. In fact, a publishable paper. Someone said, I think we could redo their paper where you don't make that assumption. So keep that in mind. One of you, that may be a great dissertation. Say, can I redo their paper? Say, to what extent did that assumption affect the results? They say, doesn't. I'm willing to give them the benefit of the doubt, but on the other hand, maybe not. Okay, so those are some definitions. Okay. Next thing, let's use Bayes' law. Okay, so you're going to see this. You're going to see some complicated math, but it's not as complicated as it will first look to you. By the way, Levitt and Porter do not use the terms eastbound and westbound drivers. They just said that one driver is D and the other driver is S. Okay. It's very helpful to me if I make it more concrete and assume there's just one road and the first driver is the eastbound one, second one's the westbound one. So Levitt and Porter don't use those words. I'm putting them in. I suggest when you read their paper, And they say the first driver, and the second, you substitute the words, the eastbound driver and the westbound driver. Write it in your notes to the side, and that, I think that will help you greatly to understand their paper. Okay, now here's what they will use. Okay, probability. Okay, they will calculate things like this: probability, the eastbound driver is drunk, and the westbound equals sober, given a fatal crash. Okay. The paper's filled with calculations like this. Or maybe the probability the eastbound driver's drunk and the westbound driver's drunk, given a fatal crash, or the probability eastbound sober or westbound's drunk, given a fatal crash, or a probability that both are sober, given a fatal crash. Okay, the paper's gonna be filled with equations such as that, calculations such as that. Now, what you should remember from undergrad probability theory, Bayes' law. Okay, so this just equals probability eastbound equals D and westbound equals S, and the two cars crashed divided by the probability that the two cars crashed. Okay, so you got to remember that. You get used to the Bayes' law. This paper does there's probably 10 times you will use Bayes' law in this paper. Okay, so remember that. Okay, now, and let's see, and crash. The denominator. Okay, now, let's figure the denominator first. Okay, so probability of a crash equals equals probability eastbound equals drunk and westbound equals drunk and a crash. Okay, by the way, so there's 4 ways we can have a crash. Okay, we have a crash and both drivers are drunk, a crash and only the eastbound driver's drunk, a crash and only the westbound driver's drunk, and a crash when neither driver is drunk. So there's 4 particular ways we can say what happens when there's a crash, and we're going to say the sum of all those 4 particular ways equals the total probability of a crash. So probability of crash equals this term plus probability eastbound equals D and westbound equals S and crash plus probability eastbound equals S and westbound equals D and crash, and plus probability eastbound equals S and westbound equals S and a crash. Okay, now first let's calculate that first term. Okay, the probability of that happening is, first, it's the probability that the eastbound driver is drunk times the probability. So, by the way, these two drivers are independent. So, it's like given a particular time at this night, um, given that the eastbound driver is drunk, we're going to assume that tells you nothing about the probability that the westbound driver is drunk. Maybe that's not good because it could be they're in a particular part of town where people are more drunk. But let's ignore that. Let's assume everything is independent. Okay, so the probability of this first event, the eastbound driver's drunk, the westbound driver's drunk, and there's a crash, just equals, and this is, by the way, this is all given an interaction. Okay, so we're conditioning upon two cars passing each other on that road. Okay, so the probability of this happening is the probability that the eastbound driver's drunk times the probability that the westbound driver is drunk, then the probability that they crash given eastbound driver's drunk and westbound driver's drunk. So this is just going to equal the probability that the eastbound driver is drunk is ND divided by ND plus NS. Okay, it's the proportion of the drivers at this time who are drunk. Okay, ND times NS times the probability the westbound driver is drunk, and that is in D again, divided by ND plus NS. Okay, now the probability of a crash, given that, remember we threw away the interaction term, that theta I times theta j. Remember Levitt and Porter said that's something on 1 in 100 billion or 1 in a quadrillion. So we're going to ignore that term. The probability that they drunk, given that we know eastbound's drunk, westbound's drunk, just equals theta d plus theta d. So it's probability eastbound driver makes a mistake plus probability westbound driver makes a mistake. Okay, now we can do the same thing for this one, this term, and that's just going to be ND divided by ND plus NS times, now the westbound driver is sober. So now the proportion of sober drivers is NS divided by ND plus NS. And probability that there's a crash is equals the probability the eastbound driver makes a mistake, he's drunk, theta d, plus probability the westbound driver makes a mistake, he's sober, so theta d plus theta s. Okay, now next term, eastbound sober, westbound's drunk, so we just write NS divided by ND plus NS times ND divided by ND plus NS times theta S plus theta D. Okay, and then the final term just equals NS divided by ND plus NS times NS divided by ND plus NS times theta S plus theta S. Okay, so that is the denominator. Okay, put that board to the side. You do the math. Okay, just do the calculations. Here's what it simplifies to. Okay, first you get 1 over ND plus NS squared times ND squared times 2 theta D plus 2 NDNS times theta S plus theta D plus ns squared, is that right? Ns squared theta S plus theta S. Okay, theta S plus theta S. Okay. And turns out we can simplify this. Note we've got, wait. Oh, I forgot a term. There's a 2 in us there. So it turns out we can simplify this. There's a 2 everywhere here, so we can just set that. So that is what the denominator equals. Okay. The denominator. Okay, now let's see. I think I'm going to stop there. Except probability. Let me go back. Probability. Okay, except I'll do this. Okay. So, for example, we want to say, what's the probability? Now let's compute the numerator, that is. Okay. So the numerator, for the first case, probability eastbound's drunk, westbound is sober, and a crash. Okay. Turns out we already calculated that. So that is this one here. And so that equals this here. So for this particular case, so remember I said we're going to calculate 4 cases. Eastbound drunk, westbound sober, the opposite, eastbound sober, westbound drunk. Both drunk, both sober. Okay, we need to calculate 4 cases, and actually we've done those on the way to calculating that denominator. So I'm going to just show you that one case, the numerator here. And so let me rewrite that. That equals so before we calculated the denominator, and now, so I'm just going to rewrite the numerator here equals nd divided by nd plus ns times ns divided by nd plus ns divided by theta d plus theta s. Okay. Okay, now we've got the numerator, we've got the denominator. Notice, so num divided by denom is going to equal, first off, we're going to have this term in the denominator and this term in the numerator. They're going to cancel out. Okay, so first the numerator is going to equal nd times ns times theta d plus theta s, and the denominator is just going to equal, I have a hunch I'm making a mistake here. There's going to be some, there's going to be some typo here. Hopefully not. Wait, let's go back. Did I write the numerator right? Okay, there is no, I scared there was a 2. There is not. Okay, so it's ns divided by that. So nd divided by ns. Denominator is going to be nd squared theta d plus nd ns theta s plus theta d plus ns squared. Wait. You know, sorry, when I wrote that theta s plus theta s, and I said there should have been a 2, I should have just said theta s. We can simplify. So now we have ns times theta s. Okay. So that is the answer. That's for that one case. Okay. You're going to need to calculate all four of those cases. And then from there, we can start building a likelihood function. Okay. But the key is I just wanted to show you some of those early calculations. So you got an idea of what's going on in that Levitt-Porter paper. When you start seeing equations like this, they're not as daunting as they first appear. Okay, so to what I'm going to end there. So I hope you read that paper, and then next week we'll go more into depth of that Levitt-Porter paper. Okay, see, except you know what? So I said this is lecture 2.10. I would end it there. Turns out there's one little point, and actually it's probably going to take me 20 minutes. In most years, I would give it in the second section, the third session. Instead, I'm going to give it in this session. Okay, so I'm going to make it 2.11 rather than 3.1. So that means session 2 is a little long, but it means session 3 will be a little shorter. Okay, so see you in lecture 2.11.